Alright children, let's continue with the chapter that we have already started, that is diffraction of light. Now in this particular YouTube video, we basically focus on the topic and that is geometrical arrangement and condition for secondary minima and maxima. Yeah, outer minima means dark fringes, maxima means bright fringes. Okay. Now this condition of secondary minima and maxima is actually observed on the front of diffraction due to single slit. Means because in the last YouTube video you learned front of diffraction due to single slit, and in that video we saw the diffraction pattern form on the screen, okay, due to single slit. Now the same case that I am going to take with this diagram, but we derive the condition, we express the condition for secondary minima and condition for secondary maxima also. Okay. Now as I said already, Fraunhofer, Fraunhofer took two lenses, two convex lenses. So in the diagram, in this arrangement also you can see there are two convex lenses. One is L1 convex lens, another is L2. And there is a slit AB. So AB is the single slit. So AB is the single slit whose width is E. So it's AB equals to E. This is the width of the slit. Okay. And S is the source of monochromatic light. So out here what is S? Is the source of what light? Monochromatic light. Source of what light? Monochromatic light. You know monochromatic light means the light of what color? Single color. Okay. Now when I make the light from a source to focus on the to incident on the slit, the most important condition in when we follow Fraunhofer diffraction is the wavefront which incident on the slit must be a plane wavefront. So how to make the incident wavefront as plane wavefront? If we keep the source at the focus. So this source is at the focus of convex lens. So first convex lens L1. So when you keep the convex lens in such a position so that the source is at the focus, then light from the source, that is from focus, incident on the lens. So after refraction through the lens, the light become parallel to each other. You know, ray of light become parallel to each other. Now when the light incident, when the refracted ray are parallel to each other, means the wavefront which incident on the slit are the what wavefront? Plane wavefront. So these are the what type of wavefront? Plane wavefront. So children, remember this, for Fraunhofer diffraction to be observed, the incident wavefront must be a plane wavefront. That's why in order to make the wavefront to be incident on the slit as plane wavefront, by taking this slit lens L1, the source must be placed at the focus of this lens so that the light gets refracted, and when this refracted light incident on the slit, it incident in the form of plane wavefront. So AB is the slit whose width is E. Now in order to observe the diffraction pattern on the screen, we have to place the screen. So screen is out here. So XY is a screen. Now this screen is basically at a certain distance from the slit. But other than the lens L1, we are taking another lens, that is L2. Now this lens is basically placed, okay, to observe, to focus the pattern, to focus the diffracted light to be focused on the screen, to be focused on the what? Screen. Okay, that's why we are taking another lens, that is convex lens, that is L2. Okay, that's why in Fraunhofer diffraction, remember this, how many lenses are used? Two lenses. One is L1, another is L2. So basically what happened when the light from this lens, when it incident on the slit, we follow Huygens principle. According to Huygens principle, each point on the slit can produce a fresh wave from which the new wave will generate, and these waves are called secondary wavelets. Okay. Now all the wavelets originating from this slit, from this part of this slit, are in the same phase and they travel with the same speed as the original wave. But those wavelets which proceed in the same direction, those wavelets which are proceed in the same direction as the what? Incident light are focused at O. Are focused at what? O. That's why this O is the position of central bright strings or central bright band. So this is the position of central bright band. I can use the word band. So that means all the bright fringes will form at O. That means O is the position of central bright band, so that the maximum intensity of light is focused at O. But as I said already just now, that those wavelets which proceed in the same direction as incident wavefront, okay, direction incident light, are always focused at O. Okay. Now since all of them, these all waves are in the same phase, okay, so they reinforce one another and proceed a center bright band. So center bright band is always formed at O. And children, this particular center bright band is also called principal maximum. We can use the word principal maximum. The center bright band is also called principal maximum. Now, most of the incident light is actually concentrated on this principal maximum. That's why the maximum intensity is always observed on center bright band. Now, children, even you can see on the screen there is a position P which is marked. Actually, P is the position of secondary maxima or minima formed on the screen. Okay, but this position of secondary maxima or minima is actually based on the path difference for the wave reaching at P. When reaching at P means definitely that wave has to be, the secondary wavelet has to superpose each other at P. So the wavelets means secondary wavelet produced from A and B, between A and B, are diffracted by certain angles. Say that angle I consider say theta. Okay, through an angle theta, and they are focused at P. Theta is focused at what? P. That's why this angle theta is also called angle of diffraction, to form secondary maxima or minima at what? P. That's why P is the position of secondary maxima or minima, and that position of secondary maxima makes the angle in which it gets diffracted, and this angle theta is also called angle of diffraction, to form secondary maxima or minima. The next thing that you need to keep in mind is that the secondary wavelet, okay, start from this various part of this slit, that is AB, okay, are in the same phase, but when they reach at P, they reach in different phases. And when they reach in different phases, then definitely there is a phase difference. And when there is a phase difference, there is a path difference also. So that's why, remember this, when secondary maxima or minima is formed at P, the formation of secondary maxima or minima at P is actually depends upon the path difference for the wave, secondary wavelet reaching from various part of AB at P. Now in order to measure the path difference, let me follow this diagram again. So this is a diagram where we can see formation of any secondary maxima or minima at P. Now if the secondary wavelet from B are diffracted by angle theta, and secondary wavelet from A also diffracted by angle theta, and this secondary wavelet are focused by this lens L2 at P, so that when they superpose each other at P, okay, then there is a path difference for this secondary wavelet reaching at P and secondary wavelet reaching from B to what? P. And that path difference is actually calculated by drawing a perpendicular line. So you can see that, children, from A to this line we have drawn a dotted line. This dotted line means the perpendicular line which is drawn on this refracted angle, and this line meet at K. So if you look at the diagram, it looks like this. So diagram looks like this. So look at it, this is A, same diagram, AB, this is K. Okay, so the line which is drawn AK, is the perpendicular line, is actually need to determine the path difference for the wave, second wavelet reaching from A to B and B to P. Okay, so look at it, this angle is how much? Look at it, this angle is theta. This angle is also how much? Theta. If this angle is theta, children, then this angle will be 90 degree minus theta, because this line and this line perpendicular to each other. If this is theta, then this is 90 minus theta. Now this is how much? 90 degree. Now we can even calculate this angle. But see, this is a right angle triangle. That's why in right angle triangle AKB, in this right angle triangle, if you see AKB, this is a right angle triangle. This angle is 90 degree. This angle is 90 degree. So in a right angle triangle, sum of these three angle equals how much degree? 180 degree. So if you add this three angle equals how much degree? 180 degree. So with that 180 degree, so it will be 90 degree minus theta, okay, plus 90 degree plus question mark, means the angle that we need to calculate is 180 degree. So 90 plus 90 is 180 degree, and this 180 cancel out, means this question mark angle will be equals to minus theta if I take in the right hand side plus theta. So that means this question mark angle is actually what? Theta. That's why I'm writing out here. See children, this angle is also theta. If this angle is theta, this angle is also theta. Now this angle theta in this triangle in this right angle triangle, in this right angle triangle, this angle is theta. Now with this right angle triangle with angle theta, we can calculate this gap, and this gap is called path difference. So children, in the diagram, this gap is actually called path difference. This gap is called what difference? Path difference. Because this wave, second wavelet from A reaches at P, second wavelet also reaches at P, but with a difference in the path or the distance. And that difference, the distance is actually measured by this BK. That's why BK is actually the what difference? Path difference. This is the path difference for the wave reaching from A to P and B to P. Now this path difference we need to measure now. Okay. Now this path difference, as I just said, can be calculated from this right angle triangle. And with this path difference we can measure the condition for secondary minima and secondary maxima. So let me just do with secondary minima. So first we go with secondary minima. Condition for secondary minima means all dark fringes which is formed on the screen. So for that I follow this right angle triangle AKB, this right angle triangle. In this right angle triangle AKB, this angle now is theta. Now this side is your base. So AK is your base, BK is your perpendicular, and AB is your what? E, that is hypotenuse. Base, perpendicular, hypotenuse. See, base, perpendicular, hypotenuse. So we have to measure perpendicular. Path difference means perpendicular. We know hypotenuse, and you know perpendicular and hypotenuse are divided by sin theta. So in triangle AKB, sin theta means perpendicular. This is perpendicular, this is by hypotenuse. So BK by AB, so if you cross multiply, BK equals to AB sin theta. But what is AB? E. That's why I have written BK equals to E sin theta. So children, to calculate the path difference for the wave reaching from A to P and B to P, that path difference BK is now E sin theta. So look at it, what is the path difference? E sin theta. Now for the first secondary minima to form at P, it is observed that a path difference BK must be lambda, must be equal to the wavelength of light which is incident. Means when light incident with a wavelength, and that wavelength of light is equals to this path difference, then we always see the formation of first secondary minima on the screen. So for first secondary minima, BK path difference must be lambda. So the angle made by the first secondary minima is given by theta 1. So look at it, theta must be theta 1. So I replace now E, theta means theta 1, so E sin theta 1 equals to, now BK I replace by lambda. So what is the first condition for secondary minima? Path difference E sin theta 1 must be lambda. So path difference must be lambda. This is for the path difference. See, as I said, E sin theta 1 must be equal to lambda for first secondary minimum. Okay. Similarly for second secondary minimum, okay, path difference must be 2 lambda, double of lambda. In that case, theta will be theta 2. So your path difference E sin theta 2 equals to 2 lambda. So for second secondary minimum to form, a path difference E sin theta 2 equals to 2 lambda. So see, E sin theta 2 equals to 2 lambda, that is for second secondary minimum. So in this way, we can calculate for third secondary minimum, fourth secondary. So in general, I can write for mth secondary minimum. So I follow the sequence. Your path difference must be E sin theta m. I write on m equals to m lambda, where m starting from 1, 2, 3 like that, the multiples of lambda. But I have put one out here plus minus sign. Now why plus minus sign I have put? Because your secondary minima is formed on both sides of central maximum. That's why the path difference for mth secondary minimum is given by E sin theta m equals to plus minus m lambda. Now in the next YouTube video, we measure the width of central maximum, and even we can discuss the condition for secondary minima. That you learn in the next YouTube video.